Spur gears are the easiest to design for and probably are the most versatile of all gear sets. They rely on parallel shaft alignment to transmit energy and can be used in many different applications. This particular model has a 2-to-1 gear ratio that would be suited for input on either shaft. This model chains gears together in order to rotate two differential units at either end. By utilizing spur gears, this differential eliminates axial forces inside of the unit during operation. This is a more conventional gear reduction unit that uses spur gears. This one uses bearings and is very smooth. Here's a very high reduction gearbox that also uses spur gears. It doesn't have bearings and is prone to melting under high RPM. Bevel gears are very useful in transmitting rotational energy across a wide range of angular misalignment. This model is set to 90 degrees. This open differential model uses a number of different bevel gears in order to perform its function. A characteristic of bevel gears is that they produce axial forces in operation. Some limited slip differentials take advantage of this property to lock up the unit using clutch packs. These bevel gears are being used to redirect power from the transmission into the wheels across a 90-degree angular offset. This contraption exhibits the ability to transmit rotational energy across a wide range of dynamic angular offset. Worm gears have two very useful properties. One, they can produce enormous gear ratios in a compact space, and two, the spur gear is locked in place by the worm gear, meaning that the output shaft will hold its position even if force is applied to it. These are both very useful characteristics. Worm gears are the most difficult to design for and 3D print, for myself at least. Largely, this is due in part to very specific tolerance requirements and large overhangs that are difficult to print. Here's an application of a motor reduction unit using a worm gear. Helical gears are technically a type of spur gear, but they have a unique property that allows them to be used to translate energy through non-parallel and non-intersecting shafts, similar to a worm gear configuration. These gears are challenging to use from a 3D printing perspective, due in part to the contact friction as well as high axial loads that tend to melt the plastic gears. When using helical gears in a parallel axis configuration, they work just as well as conventional spur gears. However, they're actually a little quieter and can handle larger loads. Here's another example of a functional crossed helical configuration. It's printed in ABS as the PLA was melting during operation. Rack and pinion gears act as linear actuators that translate rotational energy into linear, or vice versa. I haven't used these types of gears too much, so I only have these simple models to show you, but that does not mean they aren't useful. I just haven't seen to use them very often. A special characteristic of these gears is that they can be driven from either the linear or the angular component. Internal gears are another type of spur gear, but they can be used for a variety of specialized functions like transmitting energy across parallel misalignment, or for example, you can convert rotational energy to linear as shown here. I would like to think most commonly you will find them being used in planetary gearboxes such as this one. There are many other kinds of gears out there, but these were just a handful of the types of gears that I find to be the most useful.